introduction to longitudinal methods, all right? So there's not going to be any maths, and I'm not going to be showing you any proofs. I'm really going to be trying to focus on the kind of approaches that you can take given your question, all right? So given the question that you might have, and then the kind of data that you have available. And what I'm going to do is I'm going to draw upon some of my own experience. I hate to tell you how long I've been doing longitudinal research, but it's quite a long time at this stage. So what I'm going to do is I'm going to give you kind of an overview of, given your question, given the kind of data you have, the kind of approach that you might use. And then I'm going to show you some of the research, some of my own projects, all right? And I'll show you some results from some of my papers that have been done largely with lots of other people. And hopefully what that'll do is it'll give you an idea of the methods that are available to you. So the first thing will be, let me just show you the program for today, okay? So I've got a lot of different things that I'd like to get through here, but this is also about participation. This is about interaction with you, right? So what about if I go through the first few sections there about what's cross-sectional analysis and what's the problem with cross-sectional analysis? There isn't necessarily a problem. Why do we need longitudinal analysis? What is it? And then maybe if I go through the change between 2 points material, and then we stop, and then people can ask questions or make comments, and we'll have a little interaction session then. And then I'll sort of go on to event history modeling, Hasbrook modeling, before going on to the panel models, random fixed effects. And then if we get a chance, we'll go on to lane class models. And between all of those different sections, maybe we can have discussion, okay? So you're not just listening to me droning on for the next hour and a half. It would be good if everybody else gets a chance to talk as well. So let me just get going and talk a little bit about, well, what is cross-sectional analysis first, before we move on to anything longitudinal. As you can see here, okay, this is my nice little graphic that I actually stole off one of my colleagues here, Jan Skopek, for illustrating what we mean by cross-sectional. And of course, what it is, it's a time slice. Okay, you're looking at a population or some variable at a particular point in time, and you've literally taken a time slice of that, which you're then examining. All right, so the world and social processes are, as we would all know from our common day, everyday experience, they are flows. They are longitudinal. We have time operating all the time, and we are experiencing flows, but we can, as researchers, take time slices through that. And those have a great deal to recommend them. Most social research, most social and economic research is cross-sectional. Okay, there's nothing wrong in good cross-sectional research, which is being driven by the right question. Okay, so it's cheaper, and it's going to be completely effective in many times for looking at factors like prevalence, okay, or the inequalities between different groups, as I've said there about relative risks or odds differences between different groups. It's perfectly acceptable to do cross-sectional analysis, and there's absolutely no problem with that. It's not a poor second cousin to longitudinal research. It's a worthwhile and, as I say, the most common type of methodology used. But there are problems, of course, with cross-sectional analysis. All right, inferences to the population can be really problematic. I mean, those are the sort of a good example of that is where, say, we wanted to look at the hospital population in a hospital. If we go in there on one day and we go around to all the beds and we enumerate who's in there, okay, the people who we will come across and their characteristics may not be a good representation of all of the cases that go through hospitals, because we are going to be more likely to see those cases who have long stays in hospital on any one day at any one time, aren't we? those spells in hospital which are shorter and which are therefore going to be a lot more frequent are going to be underrepresented. So we're not going to have a very good cross-section of the hospital population. So a cross-sectional method isn't appropriate in that situation. The standard reason why we move from cross-sectional to longitudinal research is to do with inferring causality. Because if you're measuring dependent and independent variables at the same time, then of course it's very difficult to work out what precedes what. and longitudinal research is going to be much more effective, indeed essential, if you want to try to establish causality, which is frankly what often social scientists are trying to do. With cross-sectional data, you're going to find it really hard to separate age from cohort and period effects, okay? If we go out and we measure a population now, there's going to be younger people and older people. If older people are, say, more traditional than younger people, is that because people get more traditional as they get older, or because those older people were socialized during an earlier period when people just tended to be more traditional? Okay, we can't pull apart the age cohort differences there. So those are going to be important reasons why we might want to adopt a longitudinal piece of research where we'd have old people and young people at a previous point in time and old people and young people during a later period in time. And therefore, if we have that, then we can compare older people and younger people at different periods of time and look to see what's been happening in terms of secular change and, say, their degree of traditionalism. Okay, and then lastly, this is a more kind of abstract reasoning, but if you do cross-sectional analysis, you're kind of making an assumption here, and that is that the coefficients that you're going to be deriving about relationships express the net difference in the effects of all the predictors here. Okay, that you're seeing them, if you like, after everything has been worked out and they're in equilibrium. But of course, there might not be. There might be processes underway here. You're just not seeing them. Right, so these are all good reasons why you might want to move from cross-sectional to longitudinal analysis. So what is longitudinal analysis then? Well, here's Jan's picture, but this time made into longitudinal analysis. And you can see here now, instead of having just a time slice, we have a clip. We have a clip of a longitudinal process that allows us to examine change over time, and we can have repeated measurement of our process here. It doesn't have to be repeated measurement, of course. You could just have measurements of the entire duration there. But the important point is that you've got a longitudinal measure that begins to help you to get around some of those problems that I've just been talking about. Although just having longitudinal data, of course, isn't necessarily enough. You are going to make sure that you're asking, that you've got the right data for the questions that you're asking, okay? And then that you're applying the right methodology. That's always going to be important. So why do we need longitudinal analysis? What kind of questions can we ask of longitudinal data? Well, as I said, as one of the criticisms of cross-sectional data, with a longitudinal data, we can talk about flows and durations rather than stocks. Okay, so we can look at average length of hospital stays because we can have a population of hospital stays over a long period. And similarly, we can look at average durations of stays in hospital, or average durations of poverty, or average durations of unemployment. We can look at duration now, okay, which we can't always do with cross-sectional figures or cross-sectional data, because in the time slice, there'll still be durations which are ongoing. We can describe trajectories. Longitudinal analysis is not just about causality. Just getting good description is one of the foremost and most important characteristics of longitudinal data. If it's a longitudinal phenomena, then being able to describe it with longitudinal data is really important. Having said that, if you can then do causal analysis with longitudinal data, that's usually the next step forward, isn't it? So good science is first of all based upon having accurate and rigorous description, but then to move on to the next stage to actually explain phenomena, you're going to need to have longitudinal data. So important questions like, and these are sort of questions that I suppose that I've been involved in doing analysis on. Does maternal smoking in pregnancy lead to child attention deficit hyperactive disorders? Does breastfeeding a child improve their cognitive ability over time as they age? Did the fiscal crisis increase emotional and behavioural problems amongst children in Ireland? These are kind of, if you can see, these are cause and effect kind of questions, aren't they? They're saying, did X lead to Y, right? And what I'm going to tell you about now is, given the question you're asking and the data you've got, what kind of methods could you use? So the first one I want to come to is the most basic, but as I've said there, very effective approach to longitudinal analysis. And that's the analysis of change between two time points, okay, which we'd routinely call baseline and follow-up. this is going to be the bread and butter of most longitudinal analysis. Most people, if they're going to do a longitudinal analysis, will follow this type of model. And the classic approach to this type of study in terms of establishing causality is, of course, the randomized control trial. Right? The RCT is the sort of go-to benchmark model for looking at longitudinal effects, and it's based upon the idea that if you measure a phenomenon at baseline and follow up, and moreover, you are able to randomly allocate people to intervention and control arms at baseline, then any differences between those intervention and control arms at follow-up are going to be a function of your manipulation of the variable you're manipulating, rather than, say, prior characteristics, say people being selected into being the intervention or into the control. Of course, you randomize that, so it can't be that. But we don't always have the opportunity to do experiments, do we? And many of you are going to have observational data of organizations or individuals or families or some unit over time, which you've not randomized to, or you haven't randomized into some kind of intervention. In which case, what can we do if we can't randomize? How do we go about doing longitudinal analysis? Well, the basic logic still holds, of course, that if you have a baseline and a follow-up, well, then you can do longitudinal analysis, okay? And that leads us to this sort of like this is the basic model of change between two time points. And it's often called the difference in difference model. All right, so in the difference in difference model, you've got a baseline and a follow-up, okay? And then you're looking at some kind of dependent variable here, which is our vertical axis. You see the dependent variable y? And the idea here is that you've got a difference over time between baseline and follow-up, but you've also got a difference between groups that you're interested in. And that's why it's a difference in difference model. And the idea here is that something happened between baseline and follow-up. And what that means is that we would expect, we should have a hypothesis that then something would have happened to our two groups, group A and group B. Our hypothesis should suggest some effect that the event has on the means of group A compared to the means of group B at follow-up compared to baseline. And the straight difference in difference model is simply an interaction effect between baseline and follow-up. It's a really neat little way of doing analysis. And the good news is that you can do this even if you haven't got longitudinal data. You can do this with two cross-sections of data. You're just making a lot more assumptions if you do it with cross-sectional data. Better to do it with individual level data where you could control for changes over time in the characteristics of the individuals. Okay, because you're having to make a lot of assumptions here, aren't you, about the factors, the effect of your event, the effect of the treatment, if you like, because you don't know, in a sense, all of the other factors that might be influencing the outcome for those individuals. So the difference in difference model is our kind of baseline, or it's our basic model for analyzing change over time between two time points. But it does make quite a lot of assumptions, okay? The standard assumption is that the value of that dependent variable at baseline is not going to be correlated with the treatment, okay, or exposure. So that's a big assumption. You're assuming that the level of that dependent variable isn't correlated in some way with exposure to the treatment at some point. If your dependent variable is correlated with the treatment probability, you're also making the assumption that the factors predicting treatment are observed and measured, right? So that you can then adjust for them. You can put in some set of variables, okay, some set of adjusters on the right-hand side in the equation to be able to take account of the selection process. So that's a big assumption, but nonetheless, it's one that can be tested. And then lastly, there's an assumption that the factors moderating the effect of treatment on the dependent variable are measured and adjusted for, okay? So you've not got any unobserved factors in here, which are going to bias the estimates that you're making of the effect of treatment on groups A and B, right? So three really important assumptions that you'd have to consider when doing this. But assuming that you can make a good job at each of those assumptions, we can then go on to do a longitudinal analysis looking at the effect of some exposure to an outcome variable. Okay, now I'm going to just give you a little bit of an example here of one I did relatively recently using Grown Up in Ireland data, which is to look at whether the Great Recession in Ireland increased child emotional and behavioural problems. Okay, so it's using strengths and difficulties questionnaire data as our dependent variable. Okay, so that's about emotional and behavioural problems and change in those between 2008 and 2010. Our independent variable is the mother's report of economic strain that the household went through and change in that between 2008 and 2010. And our question is then, did increased economic strain lead to higher emotional and behavioural problems? That's SDQ, okay? So we can have a couple of different approaches to this. All right, remember, we've got a dependent variable at 2 points in time, and we've got an independent variable at 2 points in time, okay? And we've an exposure, which is economic strain. So the two different approaches you can take to this are, you can either take what's called known as a change score, and you can see here, that's the top equation there. And basically you've got the change in the dependent variable, which is here, it's SDQ, between baseline and follow-up, okay? So here we'd be predicting the change, that's why it's called a change score. Over time we'd have the intercept alpha, okay? We'd have our coefficient or change, the delta there for economic strain. We'd have a set of other predictor variables, okay, which are going to be our really control variables plus individual level error. Okay, so that will be the change score approach, and that's going to give you an estimate of the relationship between change in economic strain and change in the dependent variable, SDQ. The other approach is the regressive variable approach. Right? So here, instead of taking the difference between the dependent variable of baseline and follow-up, what you're doing is you are you've got the dependent variable at time 2, but it's on the right-hand side, you've got the dependent variable at time 1. Okay, that's why it's called the regressive variable approach. So here, what we've got on the right-hand side here, you can see we've got the dependent variable at time 1, which we can then, when we estimate the dependent variable, what we're basically doing is estimating change. And then as with the change score approach, we're estimating the delta, the change in economic strain, plus a set of confounders and an individual level error term, okay? Now, both of these, you get similar estimates. It depends upon the model specification and some other, there's going to be issues here about specification, but basically you should get the same outcomes here. There's a sort of ongoing argument about what's the best approach. And there are arguments against the change score because if you factor in error, measurement error at 2 points in time, what tends to happen with change scores is the estimates are biased down to 0. Okay, you tend to have lots of the measurement error at both points in time pushes the effect down, which is less of an issue with the regressor variable approach, but really they're going to give you much the same kind of effect. So a very simple approach to get an insight into change over time for a very important issue in terms of the effect of economic strain here on child outcomes. Look, and so let's have a quick look at some of the results. So here's SDQ, okay? I'm showing you the relationship between SDQ over time as a function of one of the variables, which is a mediator between the exposure to economic strain and the outcome variable, SDQ, and that is conflict between parent and child. It's actually a measure called Pianta in Growing Up in Ireland. And you can see here that as the level of child-parent conflict goes down, it gets a good deal better. You can see here, this is all being taken out of a structural equation model that I estimated using the regressive variable approach. And you can see here that you get an estimate that shows that the level of SDQ declines as the parent-child conflict goes down, okay? So SDQ is worse when it's higher, if you know what I mean. So a negative score here is a good thing. That means things are improving, all right? I used the regressive variable approach in preference to the change score approach, partially because of those issues I told you about measurement, but also because I was using structural equation modeling. And if you, some of you may know, if you're using a structural equation model, you've got to have the same variables in different bits of the model. Otherwise, you're estimating different things. So I was using a structural equation model. So I used the regressive variable approach. So there you go, look at a nice result. And here's the overall model that you end up in the end. So you can estimate all the different parts of this. And these were all estimated, okay, using a structural equation model, but I was using regressive variable approach. I was essentially estimating the dependent variable, which is each of these boxes. But on the right-hand side, I had each of those variables lagged from the previous period. And in doing that, I could then make an estimate adjusting for other factors, the confounders and the individual level error terms. And because it's structural equation model, you could even have adjusted for measurement error as well. I didn't do that. That's one of the benefits of structural equation modeling, that you can estimate what's known as a measurement model. So if I'd wanted to, I could have adjusted for the error in my measures of SDQ at both points in time. All right, so there you go. A nice simple analysis, okay, very effective. Change in two measures or the same measure over time. But, oops, I've just jumped out for some reason. Sorry, pushed the wrong button. Let's go back to that one again. Here we go. So,
sorry, Richard, we can't see your slides yet.
Sorry, say that again.
Your screen share hasn't worked. Could you please try again?
Oh, sorry. I'm going to have to drop down, and I think I have to pull that, put the screen up, and then say, no, share, is it? Like select one.
Share screen might be entire screen for
share.
Yeah.
Okay.
Great, thanks, Richard.
Yeah, now you're seeing a little bit of the wrong view. Ah, is that better? Can you see it now?
Yeah, that's perfect.
Okay. Now, there is an issue here, of course, about the selection problems. Okay, and I don't want to gloss over those. Those kind of change over time models. You are going to have an issue here if you've got strong selection of people into their exposure or not. And clearly, exposure to economic strain is a big issue. I was doing that by adjusting for confounders. But if you want to go down the road of trying to adjust even more strongly for those selection pressures, you can use things like the propensity score matching, okay, which is a nice, neat, pseudo-experimental approach where what you're doing is you're estimating a function, first of all, of the probability of experiencing the exposure, which here would have been economic strain, or rather recession. And then what you do is you select people who've got a similar propensity to experience that effect. But then what you do is you compare those who did experience it compared to those who didn't experience it, right? So everybody would have a probability of experiencing recession, but not everybody did experience recession. And you can compare those people with the same probabilities, but who did and who didn't. I'm just showing you a picture on screen now using, it was an example from smoking. I was looking at the effect of maternal smoking on child emotional and behavioral problems. It was actually looking at hyperactivity. And all I'm showing you here is that we're comparing those who actually smoked in pregnancy compared to those who didn't smoke in pregnancy, but they've got the similar propensity to smoke, okay? I'm not going to tell you much more about this. We can talk about it a bit later on though, if you like, but it's a handy way of trying to adjust for these things. You can also use an instrumental variables approach, okay? But you have to have a bit more luck when it comes to instrumental variables in terms of what's available to you. Again, we can talk about that if you like. So that's the change over time, 2 points in time, all right? do we want to stop there and just talk a little, do people want to sort of ask questions about that before we move on to looking at change in time?
Richard, we only have one question at the moment.
Okay.
It was, would it be possible to share the mentioned article? So I think it was the family stress model.
Yep. How would we do that? How would we share it?
Good question. We could look to put on the, so yeah, so if we could make it available on the CESL website after, if you're okay with sharing the slides, or yeah, someone has actually said what it is on the chat, so I think we're okay. I can tweet it.
Yeah, we could always send an email around, I suppose, to the people who have attended today, or to the people who signed up for the event with all of the references that I use.
Yeah,
that'd be a good way of doing it.
Yeah.
Okay, well, look, if we have no other questions on those on that material up to this
another
point.
Question from Fiona: how do you best estimate the beta weights for the prosperity measures?
The weights for prosperity measures.
For propensity measures, propensity score matching.
Yeah.
Oh, okay. Sorry, propensity scores. So the handy way of doing this, okay, is to get hold of some of the programs in Stata. You can do it in other programs as well, but what you've got to do is you've got a two-step process where you're calculating your probability of experiencing the exposure, be that maternal smoking in pregnancy or economic or recession, and you would estimate that using one equation, usually something like a probit or logit equation. And then what you've got to do is you've got to be able to match people based upon their propensity scores. And usually the software is really good for doing that. You can do it yourself if you're good with programming, but better to go to Stata, and built into Stata 15 onward are different routines for doing matching. And it'll do it all for you. And it'll give you the average treatment effect and the balancing function and all of those factors, which are really useful. Hopefully that answers your question.
So as a add-on to that was, so with coefficients taken from prior studies.
Were coefficients taken from prior studies? You mean in my paper that I did there about propensity scores?
Maybe, could we maybe unmute Fiona so she can ask the question?
Yeah, you don't have to use prior studies. That can be based upon your own data. The propensity scores are calculated from within your own data. It's not propensity coming from previous studies. It's basically the propensity, you're estimating the propensity function across your data.
That makes sense.
Right. Well, I move on to the next component.
Yeah, I think we have another question. We can wait to ask it, or
is it a quick one? Will we do it?
Sorry, too many people talking. Are propensity scores based off demographic variables, etc.? Would this be an issue where the analysis needs to control for specific demographic variables?
They could be demographic variables. They are the factors which are leading to the person being exposed to the exposure. Okay, so they should be characteristics or experiences that the person or the unit has had that makes it more likely to be exposed to the intervention or to the issue, if that makes sense. So you've got to have factors which are predictive of your intervention.
Yeah, I think that.
I think yeah, propensity score matching is it wasn't really something I was going to cover too much today, but I thought I should just introduce it as an issue to deal with some of those selection problems. Maybe we could do another session at some point about propensity scores.
Yeah, it's definitely something we could do.
Yeah.
We have one more question.
Okay, go on.
So could you explain why a structural equation model is used in regressor variable models? And that's
yeah, I was using the regressor variable, the structural equation model there because in I was using the regressor variable approach. Okay, so I have to have the lagged variable on the right hand side. I've got to, when I'm trying to estimate the child's emotional and behavioral problems at time 2, I want to have their emotional problems and behavioral problems at time 1 on the right hand side. Okay, so that I'm estimating change. In which case, I did that because I was using a structural equation model. Right, so a structural equation model, I have to have the same variables. If I'd used the change score, I would have had a different variable. It would have been the difference as opposed to the variables themselves. And of course, the variables make an appearance at different points in the structural equation model, if that makes sense. You'll see it in, if you look at the paper, which I'll circulate, then you can see this in the paper itself. It's actually detailed as well as to why I use that approach.
Excellent.
Right. Okay. Well, let's move on to the next kind of approach then. Okay. So, what if your time to change matters? So in the approach I've just been talking about, that's change over time, isn't it? But I'm basically looking there at the mean differences over time, and I am trying to quantify the mean difference in the person. Okay. Or I might be estimating the probability of change from state J to K. All right, so I'm just there estimating a probability. Did they change from J to K? But what if the time between transition from J to K matters as well? What if that's an important factor? Well, then you have to think about changing the approach you're using away from this estimating change over time approach, the baseline follow-up approach here, to something which actually brings in durations. All right, so this is it's often called a duration analysis. Okay, and it's things like questions like this. Okay, what factors predict duration in poverty? What factors predict that you're going to stay in poverty as opposed the time that you're going to stay in poverty? What factors predict how long you're going to stay in unemployment? What factors predict when you're going to get married after you've conceived a child, if you're going to get married after you receive a child? So these are questions about duration, aren't they? They're not questions about the probability of change. They're about how long it takes to happen. In this case, you've got to adopt a different kind of approach. You've got to measure time itself, and you've got to use a sort of class of analyses called hazard rate or event rate models, or event history models. Sometimes they're called survivor models or failure time models. They were used an awful lot. Initially, they were used in the cotton industry to model how long a cotton thread lasted on a machine before it broke. So these bring out a whole class of sort of problems that we need to look at. Okay. Oh, I didn't realize I had any. There we go. So here, what we're looking at are sets of data. Okay. And I just wanted to show you the data structure first, so you get an idea of it before I show you the approach that you take. But you've got different cases, and you can see here I've got 12 people, all right? And what I'm giving you is I'm giving you the time that they were in some, we would call it a state space, but they were in some kind of condition. They were in some kind of position. And you can see the time there in months varies, doesn't it? So case one's got 24 months, case two only has 6 months. And then they vary in terms of their sex, 1, 2, male, female, and their age. And then crucially, look at the final column. Were they censored? Okay, and what does that mean? That means that we observe them before they got to the end of their spell, right? So if the censoring is 1, then we observe them in the data before they'd actually finished their spell. So if you think about it, you can see case 3 there, the spell length is 17, isn't it? But that person is censored. So it might be that their actual spell of whatever this is longer than 17 months because it wasn't actually at an end when we observe them. So we've got to think of different kind of analysis for this. And this is where event history modeling comes into its own, right? So the problem is that as the spell of poverty, whatever it is, may be ongoing observations, spells can be censored. So how are you going to cope with this? Well, you can't do it just by using the total spell length, okay, and then regressing on a set of characteristics, because for one thing, the spells might be an awful lot longer, and if the factors that you're using as predictors are correlated with them being with their length, as they should be, because you're using them to estimate it, the chances are that it's going to be biased, okay? Because the spells could have started and stopped at any point during your observation window. So we need to find some other way here of estimating this rate of change, as it's called, or propensity to move from state J to state K. Right? So the answer in event history modeling is that you use the rate, okay, the rate of transition. And that's different from the underlying metric, isn't it? So the underlying metric would be months, but a rate is, we usually think of rates, for example, when we're thinking about, say, incidence rates, you know, like during COVID, for example, out of a population, you've got a rate of people being being tested out of 1,000 or 10,000. Here, what the rate is transitions in a given month, okay, relative to those who are exposed, right? And that's exactly what this little equation's telling you. So we use a rate based on the number of transitions in period T relative to the number who was still exposed at T, okay? So here, the probability that the transition occurs in the interval from T to T apostrophe, okay, it's the probability that that occurs, given that no transition has occurred already between 0 and T. All right, so that what we're looking at is in every time period, you've got to look at the unit of time. What's the probability you're going to make a transition here? And from the risk set, the denominator, we take out those who've already been censored. And we're only looking at those who are still in play in that situation. So an event history model here is looking at the rate between those exposed to those who are making the transition, and it's within each month. And we can do that for each month and then plot the hazard rate. Does it increase? Is it plateaued? Does it fall? They're often called log linear models because you log the probability so that you can estimate it using sort of standard maximum likelihood kind of approaches. All right, let's look at a little example. So, oh no, it's a bit wobbly. This is plucked out of just a paper of mine from a very long time ago, sometime in the late 90s, which was looking at unemployment durations. These are exits to unemployment in the Netherlands, okay? And we were comparing countries. So we had Britain, the Netherlands, Germany, Italy, I think it's just those four. And Sweden, we had Sweden in there as well. And we were looking at how did the probability of exiting from unemployment change given the length of the unemployment spell. And what you tend to find is that the probability of leaving unemployment reduces the longer the unemployment spell because of a number of important factors to do with selection out and other factors, okay? But my wobbly picture here shows you that you can see it moves around, but you can see a decrease over time there. Now, so that's sort of an example of this kind of transition data. And usually for these kind of duration models, you would have retrospective spell data. Okay, so you'd know about how long the spells were, but you don't have to do it using these kind of retrospective spell data. You can do it using data from panels. So panel data, if you haven't come across them already, panel data are data which you are collecting from individuals or households or whatever the unit is, and you're collecting them at a regular time period. So you're going back to them every year. In the case of, for example, Understanding Society or the German Socioeconomic Panel, or you're going back to them over different time periods, okay? And what you can do is you can then stack those up together, and they give you a kind of like they give you a measure of the duration of spells, but you have to make a few kind of assumptions to make this work, okay? So if you do this and you make these assumptions, you can then apply some of those duration rate models that I've just been talking about. So for example, here's a panel with 7 waves, okay? Just a notional panel. And I've got 2 states here, 2 state space, people who are not in poverty or people who are in poverty. And you can see that this is one person, right? And you can see for spells, or when we observe them at T1, T2, and T3, they weren't in poverty. But in T4, 5, and 6, they were in poverty. And then in T7, they then moved out of poverty. Now, we are making an assumption here, aren't we, about the fact that they were in poverty between the observations. But if you make that assumption, which is not too massive an assumption, you can then assume here that you've got a spell of 3 time periods, 3 years, when that person was in poverty. And if you've got that, you can then start applying duration models to examine this. And that's exactly what we did in this paper, myself and Didier Fouage, back in 2005, when we used data from, at that point, it was the European Community Household Panel Study. And we used 5 waves of the ECHP to look at these pseudo spells of data, okay, which they were used, we sort of created spells from the underlying 5 waves. And then we used hazard rate models, as well as another technique, to look at the exit probabilities from poverty. And the patterns that emerged from this were really interesting, because of what you tended to find is that those countries in Southern Europe that tended to have higher cross-sectional rates of poverty, they also tended to have more persistent poverty at the individual level and household level, and that people were more delayed in exiting from poverty. And the same thing was true in the US when we were comparing our European data to US data. So it was a neat little, you have to start thinking about time as a variable in itself, as opposed to just thinking about change. And it's a neat way of using available data from panels to look at that variable of data, of time in itself. Adjusting for the fact that some people are going to be censored when you observe them, that they will have still be in the spell of poverty when you observe them. Will we just move on to the next set of issues, because I think we're probably going to run out of time, aren't we, if I go at this speed?
Yeah, that sounds good, Richard.
Yeah. What time are we now?
We're coming up to 3:25.
Oh, okay. So we've already been talking for an hour. Right. So let's move on to panel and cohort data, right? So I've already introduced you to the idea of panel data. Cohort data are fairly similar. So panel data tend to be a cross-section of a population. We take a measure at one point in time, and we keep going back to those people over time, often every year, but sometimes less frequently. And cohort data are very similar, except with cohort data, what you're usually doing is you're choosing a group of people who share some characteristics. So for example, in growing up in Ireland, they were all tended to be 9 months when we first saw them, or they were 9 years old when we first saw them, and then we subsequently follow them. They're a cohort of people. Now, panel data, as I've said, and cohort data, they can produce really rich longitudinal information for describing trajectories and analyzing the factors that explain change over time. If you're lucky, and if they've collected the right data, you get lovely repeated observations of the same variable at the level of the individual, maybe at the level of the household. And what this means is you can use multi-level models to both model the trajectories that people are following, okay, and the factors which are predictive of change, because you've got multiple observations per person. Think of their observations being clustered within the person. And you can even then look at people within households. Okay, so if you've got multiple people in a panel study in the same household, you can look at multiple observations for each person and then multiple observations within each household. It's a lovely hierarchical structure. So here we can model individual variation in growth using growth curves if we want to. And that's exactly the approach that I've used in a number of papers. in these multi-level models, you can use repeated measures, and they don't have to be equally spaced out. They don't have to be balanced in the sense that people can be there for part of the observation period, but not for all of the observation periods. And some of the approaches I'm going to show you are robust to this. They're not biased by the loss of people to the sample. And then you can use explanatory variables on the right-hand side that can be both time invariant, things like gender, for example, or time varying as people get older, or they can be, say, income. It can be time varying, okay? So let's look at how that might look. So here we've got a panel, okay? And I'm just putting forward a variable here, which is child weight. So on our y-axis, on the vertical axis, we've got child weight, and you can see we're measuring it at 4 points in time. By and large, children tend to grow, as you know. All right, so you can see our curve is upward, isn't it? We've got 4 observation periods, and in each period, they're getting heavier with child weight. Now, to deal with this, right, we now have to think about how our data are clustered hierarchically, okay? So we've not just got individual observations here, they're correlated, aren't they? Because each of those observations is clustered within the individual. So we have to think here about modeling this, taking account of the correlation between these things, between these individual observations, which is the individual. And we can use our multi-level model structure for this. And multi-level models are a version of what's known as a random effects model, right? And why is it called a random effects model? It's a random effects model because it uses unobserved random variables to achieve that clustering of points within individuals. Okay, so let me give you an example here. Okay, so if we've got our 4 observations of the child, all right, and you can see that by and large the child gets heavier with time, don't they? But notice that the children themselves, some are heavier than others, aren't they? Some are, they clearly are vertically arrayed here. And we can take account of the difference in the mean weights of these children, the intercepts for these children, using an unobserved random variable, okay? So it's an unobserved random intercept. And the assumption is that we're drawing that from some distribution of population, all right? So we've got an underlying population and we're drawing a random sample from it. And the reason why we make that assumption is because then we can apply our standard tools about variance, because we're assuming a normal distribution. So we can assume the normal rules about how variance works within a normal distribution, and we can decompose it, okay? So within a random effects model, you've got a random component for the random intercept for each person. But each person will possibly also have a different slope. So not only do they have differences in their intercepts, but they may even have differences in their slopes. And what do I mean by that? I mean that some people are going to be growing more quickly than others. Some might even be losing weight over time in some set of circumstances, okay? And here we can now parameterize, or rather not parameterize, but we can have an unobserved factor, which is the slope for each individual as well. So we can have a random effect for the intercept, and we can have a random effect for the slope. And because we can make the same assumptions about the slope coefficients as for the intercepts, we can decompose that as well and have that within the equation. And that's exactly what we do in a multi-level model if we're estimating these random effects. They're often called mixed models when we do this. And they're mixed because we have random components, which are our intercepts and slopes. And we also have fixed components, which are say, covariates like gender. Okay, it's not drawn from a random, from a population distribution. It's just drawn from, it's a characteristic that only has 2 levels. So you get the idea, you've got random and fixed components there. We'd be estimating the parameters for the fixed components, but estimating the variances of the random components. So let me just show you a sort of an example of this, all right? here's a multi-level structure that brings together observations for the same individual over time. All right. You can see here I've got two data structures. You can, at the top, I've got the observations nested within individuals. Okay, there's ID1, ID2, ID3, ID4. And some of these people have got 4 observations. One's got 3 observations, one's got 2 observations. And on the left-hand side, I've displayed these in wide form, it's known. So you can see that person 1 has 3 measurements of height, and they go 75, 85, 95. I've got 3 measures of age, and they're a female. So now that level, you can see the nature of the data, but it actually won't be much use to me in terms of estimating these models, because I need to have them in what's known as long format, which is on the right-hand side here. And there you now have each observation in terms of the person has a number of individual observations going vertically down the page. And I am then able to estimate the one equation for each of the people, okay? And because I can then estimate those random intercepts and random slopes, we're going to get a coefficient, an unbiased coefficient of their characteristics, the effect of those characteristics. And we can see how the effect of those characteristics have, when we estimate them, on the underlying variance at the individual level as opposed to the observation level. And that's important because now we can look at how much of this variation is explained within individuals rather than between individuals. And that's an important transition. Now you're thinking about how much is being explained by the trajectories and the factors that predict trajectory within individuals as opposed to differences between individuals, okay? Now this approach is a really useful approach that I've used, and I'll come back to an example in a second. What are the assumptions of these random effects models, these multi-level models? Well, we've got observations that are clustered within people, okay? And we're making the assumption here that intercepts of persons are a random sample from a larger population, and they're approximating a normal distribution. So you've got to have enough of your level 2 units to justify that assumption. So quite often people, for example, they use data on individuals within countries, and then they only have something like 15 countries. That's rarely a random distribution, okay? Whereas, say if we think about growing up in Ireland, where we've got 8,500 individuals, if we have 3 observations for each of those individuals, that's a random sample of children from Ireland in a sense. So your assumption there is met. There's also an assumption here that those between person errors, so between the different people, are uncorrelated with the independent predictors in the model, okay? So those residuals in terms of the intercepts, right, that the assumption is that they're not correlated with your right-hand side predictors. And if this assumption isn't supported, then your estimates are going to be biased, all right? The question is, are between individual error residuals, those errors, correlated with the predictors of within individual variation? And if so, you've got an omitted variable in there somewhere and your estimates are biased. If you want to do tests for this, then you've got to specify things like a Houseman test, okay? And that'll give you a test of whether this assumption is warranted. So I've got sort of an example of this in terms of a study of socioeconomic variation in children's body mass trajectories in 3 contemporary European countries. This is work I did with Cathal McCrory, using not only Growing Up in Ireland, but also Generation 21 from Portugal and Millennium Cohort from Britain. And basically, we use those different data, combining for GUI, we use different cohorts. This is what my point I made earlier on about it's really robust to the numbers of waves or observations that people have. And then we did an analysis of BMI over time using cutoffs as well for obesity. And we were basically looking to see whether there were there were differentials in terms of BMI trajectories for children whose mothers had different levels of education. This is the growth model itself. You don't have to worry too much about this. The main things to look at here are that we've got time in here. So we've got estimates for the main effect of time being entered explicitly into the model. And then we're giving the a polynomial for that, okay, the quadratic term, which is the square of it, so that we can look at change in the effect of time on growth patterns in BMI. And notice here, we've got our unobserved individual effect, that's the intercept, U0I there. And then we've got the slope coefficient. See the U1 at the bottom? And I probably went on a little long there. Sorry about that, guys. Hopefully it looks like you got to ask all the questions you had anyway, which is good. If anybody has other questions, maybe you could email them to me. I'm just layter@tcd.ie.
Excellent, Richard. Thank you.
Okay, well, look, have a lovely weekend, everybody. And good luck with your longitudinal analysis. And hopefully we have sparked, maybe galvanized you into doing more analysis and getting hold of some longitudinal data. Thanks, everybody.